Hello everyone, welcome to Easy Learn. I'm going to continue my last topic on the forward bias. I'm explaining the forward bias conditions and how to forward bias a diode. I'm using the battery biasing the voltage V bias volt and R limit resistance. I had used a positive. I connected in the sequence the positive with the P side or a positive with a positive and negative with the N side or N region or negative with the negative. This is the condition that must be fulfilled. First condition with the forward bias, and the other condition I had fulfilled, the barrier potential must be greater than 0.7 volt. We had discussed these things already in the previous episode. Without wasting any time, further moving to complete this forward bias condition and its effects and its how it works, and fundamental picture we must have to draw for complete understanding. I'm going to draw the fundamental picture. What is the fundamental picture? Basically, in a fundamental picture, we are basically considering the electrons in detail. For example, this is a diode, and here it is a barrier potential or depletion region. This is a barrier potential. For example, barrier potential. This is a barrier potential or a depletion region, and here it is metallic leads are already connected. For the connections, this is the negative terminal. We applied the negative to this side and positive to this side. This is the P region, and this is the N region. This in the N region, in majority there are electrons in excess, and there are very few holes are also available. Majority carriers are their electrons, and minority carriers are also available, and there are holes. I'm not basically trying the minority carriers to avoid the confusion here. Basically, I'm just focusing on what happens when we bias in this condition, in the forward bias with the positive with the P region and negative with the N region. Basically, my focus here is to discuss this. For example, I draw many negative here, and this is negative layer here, and many holes, lot of holes. Enough now. And there are electrons. Now going to explain what is this. Some here too. Okay, now this is the fundamental picture of what happens when a diode is forward biased. Because you know that the like charges repel each other. When I connected with the source, this is the negative potential, and negative is connected here. Like charges repel to negative side of the bias voltage source is the negative side of the bias voltage source here pushes the free electrons, which are the majority carrier in the N region, towards the PN junction. This is the PN junction, and pushes towards means they push, because this negative and negative pushes and push towards this PN junction. Their movement is all electrons are now trying to move this towards this side and in a fixed pattern. And what happens now? Majority carriers are moving in the N region towards the PN junction. This flow of electrons is called the electron current, because there are two types of current, as you know that the electrons are moving in this pattern. And now I'm going to say that this movement is due to the free electron. So this is the movement of the free electron. The negative side of the source also provides a continuously providing a free electrons towards these sides, not for a while, but it is continuously we had connected to this. This is a continuously moving pattern, not a still that we had connected for a while, for an instant, and then disconnect this. This is I mentioned here that this is continuously provided with the free electrons. So there is a source which is continuously providing free electron. This is an electron current, and electrons are flowing through the external connection into the n region, as this is shown, and arrowheads movements. The bias voltage basically imparts the sufficient energy to the free electrons for them to overcome the barrier potential. This is a barrier potential, and it is of the 0.7 volts in silicon case, and their barrier it provides the enough energy to overcome the depletion region and move on through into the P region, and they will move and or jump this energy hill. This is like an energy hill they have to climb. When the bias voltage previously from here pushes, and they basically cross the barrier potential because of the bias voltage push. Once in the P region, when they reach in the P region, these conduction electron, they are basically free electron or conduction electron in the conduction band, have lost enough energy, because when they pass from this they had lost their energy, and whenever an electron lost their energy, they come toward back in their conduction band. They come to the conduction to valence band, because the conduction band, when in the conduction band, they are free electron and is available for the covalent bonding and other reactions, and to conduct. And when they come in the valence band, they are not able to conduct or take part in the chemical reactions. The conduction electron have lost enough additional energy here to immediately combine with the holes in the valence band. Holes are also better in the valence band, and now the electrons are in the valence band in the P region. Simply why? Because they have lost too much additional energy, overcoming the barrier potential to remain in the conduction band. So unlike charge attract, the positive side of the V bias voltage source attracts the valence electron toward the left side. So they attract toward the left side. It attracting towards this side. A movement is towards the left side. Positive side, here is a positive and here is a negative. It will basically attract the hole in the P region, provide a medium. These holes provides a medium or pathway for the valence electron to move through the P region, For example, this electron basically provides now the valence electron moves from one hole to the next towards the left. This valence electron moves towards the next. For example, valence electron move from one hole to this electron in the next step, come here and fill this vacancy, empty space, and the hole comes here. Definitely when there is this electron left his space, there is definitely a vacancy left. This is called the hole. The holes which are in majority carried in the P region, these holes are in P region, effectively move. These holes are basically holes moving. When holes are just when the electron come here and then here, and electron, because positive and negative are attracting each other, so the electrons come here, and when they move and go out of this semiconductor material through the positive terminal, while due to this movement the holes are moving towards the right side, because when electron come here, these holes moves toward this side. So this whole the movement of the holes is called the hole current. So next is when this movement occurs, basically the effect of the forward bias on depletion region must be discussed. What happens to the depletion region? For example, I discussed that this is a this is a PN junction, and for example I say that this is the depletion region. Before biasing, I had not biased, as you will see that this is P and this is N, and when first I draw this diagram and then I will explain. Basically English is not my mother tongue, or it's basically tough for me to explain in English, and I will try my best, but it's not very good. You have to manage it, because I'm trying my best. I will try to learn more about English, so try to understand this, don't mind please. Okay, coming back toward the point, as the more electrons flow into the depletion region, in the more electron are moving into the depletion region, the number of the positive ions is reduced here, because this is basically this depletion region. If I want to explain here, this is just like the layer. This is just like a layer, which already explained in the introduction to electronics episodes. This is just like the layer of the positive ions already here, and this is a layer. When electrons are moving from due to the push of the external source, and they move through the depletion region, the number of the positive ions is reduced due to the movement of the electron, as the more electrons are moved. Even the holes effectively flow into the depletion region. Holes also move into the depletion region, and they reduce the electrons. When the holes move into the depletion, the number of the negative ions also reduce. So the both sides, both things are reduced. This will cause the basically in the forward bias case, this will results in the narrow of the depletion region, reducing the width of the depletion region. This will cause, this is the reason when the depletion region is depletion region basically loses its width. And one more thing I want to explain here, what happened with the effect of the barrier potential during the forward bias. Barrier potential, this is the depletion region. Now what is the effect of the barrier potential? As you know that this is the 0.7 volt energy hill. Recall that the electric field between the positive and negative ions in the depletion region on either side of the junction creates an energy hill. Basically this is energy hill that prevents the electron from diffusing across the junction when equilibrium, and this is basically the barrier potential. So barrier potential is what? This is nothing, a energy hill, the energy hill of 0.7 volts, you can call it, explain it in simple words. So when the forward bias is applied, the free electron are provided with the energy hill from the bias voltage source to overcome the barrier potential and climb barrier, and they are basically jumping from here, and 0.7 volts are basically required to, or higher required to move from this. In other words, the electron give up an amount of energy equivalent to the barrier potential. This biasing voltage equal to the barrier potential 0.7 volts, as I indicated. 0.7 volts are must be required. So, and you can say that this will lose the energy. The electron when come here from moving from the depletion region, it will lose the energy of 0.7 volts. So for example, I'm using the 5 volt battery, and when it move, the electron are moving from this, and with there current will pass, definitely voltage pass, but the 0.7 volts of drops happens. This is because of this barrier potential or energy hill. And moreover, one more thing, this is the main thing is this 0.7 volts drop. And one more thing, additional small voltage drop occur across the PN junction region due to the internal dynamic resistance. These are the dynamic resistance, and it is very small. Dynamic resistance are basically very small. Dynamic resistance, these are very small, and this factor is usually neglected. This is basically discussed, and this is not, this is, even in higher cases this is also neglected, but in I am not neglecting this in my coming episodes. I will focus this 0.7 volts, and this is a very small dynamic resistance is neglected, but will be focused in the even dynamic resistance. We will focus on the dynamic resistance too in the coming episodes. The forward bias is completed here. In the next episode I will discuss about the reverse bias. Thank you very much.